So it's my great pleasure to welcome Robert back, Robert Holt, who is Joint Team Leader of Electrical Engineering, Green Technology Team at Callaghan Innovation. We had you along 2 years ago for an energy technology event looking at commercialization. And so it's great to have you back today, and you're going to be talking about the Internet of Things and low power wide area networks. Yes. So I won't take any more time.
Thank you very much, Owen. Yeah, thank you. Thanks everyone for coming along. Yeah, a bit about myself. I used to be the team leader for the Green Tech group and what was IRL and then became Callaghan Innovation RTS. And we reorganized a little bit more around our disciplines a couple of years ago. I'm going to just talk a bit about Callaghan Innovation. Our purpose is to enhance innovation and accelerate it in New Zealand. So we have 3 threads that help us do that. One is we have business improvement, which is basically about better by lean, managing IP, helping digital companies start up. We run a series of incubator programs for that. And if anyone's interested in that, I can connect to my colleagues. It's not my strength, but I know the people to talk to. The other part of our business is the funding. Now this is basically, we administer the growth grants, which will probably soon turn into tax rebates, but essentially they say they're money to companies who do a lot of R&D. The project grants are the next level down. These are grants to solve a particular problem or to develop a process, particularly around accelerating that innovation inside New Zealand. And they go to a very wide range of companies doing a lot of interesting things. And I'm very proud of my colleagues. They've done a lot to get the process slowed down. So instead of taking months, we're talking weeks. And it's a flexible process. And I'm told it's getting better and better in terms of being responsive. It's still these are all funds we have to contribute. So with the growth grant, the company pays 80%, we provide 20. With the project grants, we provide 40 up to a limit of 800,000, 40%, and then beyond that it becomes 20. So these are projects, big projects, $1 million projects where we can provide a significant amount of the heavy lifting. And this is about helping, as I say, people accelerate. And then at the lower end, we have Callaghan Fellowships, which is actually to help academics to get started with businesses. You can ask me more about those later on, but there's sort of 3 threads on the funding side. But the piece that I represent, and I'm proud to work with, is the research and technical services part of our business. And so what we do is we provide technical help with basically consulting engineers in effect, guns for hire, to solve technical problems for companies. And so our first role is to work with companies to solve their problems now. And we work with a vast range of companies doing everything from innovative biotechnologies through to advanced materials. And my particular group is advanced manufacturing. And that includes mechanical engineering, mathematical modeling, flow modeling, hydrodynamic modeling, stability. And in my piece, it's about electrical engineering. And our current focus is very much on Industry 4.0, which I will talk a little bit about. And it sort of fits under the Internet of Things. That's our future looking. In the past, we've worked on a range of projects, including wave power, cryocooling, so cooling liquid nitrogen for high temperature superconductors, and my personal favorite, hydrogen technology, so locally generated hydrogen as a energy source. But that's really our legacy, and we still support those as required, but that's our legacy. And what we're looking now is more about what's coming over the horizon. So part of what we do as a government agency is look to what's coming 18 months to 2 years out and say, well, how should we prepare ourselves so we can best help people for the coming problems? And that's how we came up with some of the bits I'm going to talk about today. A huge amount of work around the world, huge investment, and I'll show you some of that, and a huge opportunity for New Zealand companies. And for some companies, they're already out there doing well. Other companies are just learning what to do. So I'll just get started with the definition of the internet is just a network of computers. It started for DARPA, for military purposes. It extended to portable devices, smartphones and the like. And as soon as it went to smartphones, people thought, well, we can add something to our smartphone. Let's make add intelligence around the edge. And then we get things like smart thermostats and flow meters and pressure gauges. And what I've coined is the IoT of the future, which is basically networking any device with the caveat that there's some value to be added. You can put an internet connection to your fish pond lights, but I don't see there's any real point to it, but it's possible. But there's a lot more things where we can add value, and I'll explain a bit more how that value gets added. Because what the Internet of Things, the things bit does is just allow connectivity. So it makes something be able to report what it's monitoring or controlling, and to have value, you've got to do something with that information. And there's several other players that come in to make that make that work. I just want to say, well, how is value added? It's just an example to bring it home. So what IoT allows you to do is allows you to get information, and information allows you to make better decisions. There's two quick examples. This is the weather radar from the storm in the 20th of February. And because of better information, people in the Pacific were able to get to shelter, things that could be fastened down were fastened down. And I would surmise that hundreds of people were probably saved because of that. They were able to get to safe places, and probably tens and maybe hundreds of millions of dollars of property were saved because of that. So that was an example where connectivity allowed good decisions to be made. The dissemination of that information in things like this website allowed people to use that. A more sort of almost a down-to-earth one is the second one. This is an example of a company in the North Island who provide services for farmers. They measure the temperature and the moisture of the soil. And when it reaches the right point where grass can absorb nitrogen, then they phone the fertilizer suppliers, who then comes that morning to put the fertilizer on. And previously it would be done just on a schedule. It would just be done on a calendar date. They're going to deliver 70 tons of fertilizer such as today, whether it was ready or whether the soil was ready or not. It might be late. Maybe it should have come the week before. But the more often an environmental impact was when they put it on early and the soil wasn't able to take it off. So when the rain came, it would just wash it off and cause a waste of money for the farmers, but also an environmental problem for the rivers. So this is one of those golden things where it both saves money and reduces a problem in one hit, and it's done through having sensors in the ground to provide information in a timely fashion. A bit more context for the IoT for development. So the Internet of Things spills over into lots of areas, and what I've shown here is Industry 4.0. So I call Industry 4.0 is like the wired Internet of Things. This is connections to make things, to improve process, to improve productivity, to improve flexibility of manufacturing. And then the other part is like what I call the remote control. And deliberately, remote control's been here a long time before IoT, but the Internet of Things allows the more modern connected devices to do more with that connection. And when you've got things devices, you're able to go, that connection doesn't just bring data in, but it takes it to a cloud where you can process it, you can run data analytics, do longitudinal studies, you can model, and the output of that is data-driven decisions. For instance, evacuate when there's a storm coming, an obvious example, but it can get much more sophisticated than that. So there's a bit of the context. Now, various colleagues of mine have got a lot of more experience in Industry 4.0, and just a bit of a plug, we're actually doing a trip taking people to Chicago in June. I think unfortunately it's all filled, but we're taking people to what they call the Internet of Manufacturing show in Chicago, where they're going to see the latest people applying this technology in a factory. And the outcomes of that are quite profound. There's a company, Bosch, who make all fuel injectors and things. They applied artificial intelligence and machine learning to improve their processes as a result of this connectivity. And they were able to achieve a 35% cost reduction by process enhancement. So they didn't have to spend any money. They just had to do what they did more wisely. And the artificial intelligence and the big data analytics enabled them to find the savings, which no one person could possibly find in such complicated processes. So that's one of the benefits. The other one, which a lot of people might know about, is Google applied their own DeepMind artificial intelligence to their own cooling work for their server rooms, and they saved 40% of their cooling by understanding better what they needed. So there was no compromise or loss in service. They just were smart about how they cooled what they did, and apparently exceeded their own expectations of what they could do. So this has huge environmental impacts. If you think of the energy bill for Google, most of that would have been electrical energy. That would have been a huge impact in reducing their carbon footprint, their electricity bills, and enables them to be a green company because there's less they have to convert. So Industry 4.0, very important growing area. And one of the trends that comes out of that, sorry, I'm rattling on because I haven't got a slide for this, is that Industry 4.0 is a term coined as the fourth generation. So if you think Industry 1 was Newcomb and the first steam engines, where you had a bespoke machine that did one job, and if you want the next machine, it would be different. And Industry 2.0 was when you had mass manufacturing, when you had the Ford cars, everything was cookie cutted. The number of variants went down, but the volume went up hugely. Industry 3.0 is like when they started to robotize these things, say, well, these things could be controlled and coordinated. And then you get more flexibility in the manufacturing. Industry 4, in a sense, closes the circle and gives you the ability to have really short runs of whatever you're making, have lots of variation, everything cut, and effectively it allows customization to come right down, but still be an industrial process. And so that's one of the things which comes out of Industry 4.0, and there's other things as well. The IoT ecosystem, I apologize, this is very complicated, but in fact, the complexity tells the story really, that there are so many aspects in this IoT ecosystem. Along the top, really it's about computing, so it's cloud computing, edge computing where people are doing processes and adding value by taking data from the cloud and then returning it to the cloud with enhanced information. Connectivity management, which is, I'm going to talk a little bit more about. This is how you actually get that information in and out. Traditionally, that's in the factory in Industry 4.0. It's Ethernet connections, so it's copper connections, but more and more there's wireless and traditionally cellular radio, short range wireless like Bluetooth, Zigbee, and then the low power networks, which I'm going to talk about a bit more later on, which is the coming thing in that area. The data collection and the hardware, it's everything from the swipe terminology in the shop, the pay as you go, and a lot of different bits and pieces. And then inside this network are things like big data analytics, and a lot of different on smart energy and smart grids, a key part in there. The advent of Bitcoin for managing energy transactions as well as financial transactions come down there. And at the bottom, the little ring around the bottom is the IT network security. And in many ways, that is the Achilles heel or potential Achilles heel in all these systems, but also it's a huge opportunity for New Zealand businesses. New Zealand businesses are leaders in some of these things, and we provide some of these services where if we can be proactive with our IT security and work with the best people, it's an opportunity as well as a threat, but it certainly is the bottom of the tree. Yeah, something that could choke it off if it went badly wrong. So what's the size of the business? So we're talking about a business that's $3 trillion in 2014, going up to $9 billion in just 6 years. So it would be one of the biggest growth areas ever in terms of business size. And it's happening worldwide, and it's not just in the first world, because it's predominantly the first world, but there are also applications in the third and developing world. And it's coming. Forbes have predicted this, and there's every indication that they're right. So I guess there's, why? Well, how can this be? How can it grow that rapidly? And essentially, it's, as most people know, it's just the real cost of computing falling so fast. And so you can't really see, but this is the equivalent of an iPad 2 that in 1950 is $1 trillion US dollars, or a UK billion US trillion dollars, which is down to $1,000 by 2010. And that computing power, both locally in the node, but also on the cloud, enables people to do so much more that it makes it worth connecting things. The other graph on the right is more a prediction. This is the number of devices which are connected. So already by 2015, there are 15 billion IoT connected devices, and they're scheduled to grow fivefold in 10 years. So what it means is that if you've got something that, and you've got some service in the cloud that you want to analyze data or learn from it, there's a host of things you can connect, and you need a transmission medium, and then the actual software, the cost of processing to get value out of that data is looking to continue to fall. So it's worth doing that. So the next one will give us a bit of an example. This is an example of an environmental case in America. This is a river in America where they're putting sensors to measure turbidity and acidity and the other qualities of measurement in the river. So this device is a wireless device, sits in the river. In this case, it's actually, this one's on the river floor. They can be floating, do whatever things. And this uses what they call low power wide area. I add the N, but the source didn't, so I've kept the N up. But this is low power wide area network computing. And in this case, it's actually monitoring. And the interesting thing about this is how it's an example of the whole loop close. So you've got a sensor in the field wirelessly communicating. And then in the next slide, I'll show how the data is presented. So then you've got a dashboard, which gives you historical data, current data. In this case, it's turbidity, conductivity, dissolved oxygen. Dissolved oxygen is the other one I meant to say. That's another very key measure of the health of a river. And this is very topical for New Zealand. There's a lot of challenge and a lot of work around keeping our rivers clean and monitoring them. And to know how you're doing, you've got to have data. Otherwise, it's just conjecture. Just looking at the river and saying it looks horrible doesn't tell you how you're doing. And it doesn't tell you when you're progressing or when you're getting worse. This couples the measurements with the geographic information. So you can see on the right-hand piece, obviously there's 4 places there where one of them is a yellow. So one presumes that's a case where the the parameters being measured are falling beyond the desired limits. And this is it actually democratizes data, because this being put on the web has the potential to be a school kids project. It can be information for the regulator. It can be information to the farmers and those possibly liable for prosecution. So it's time to pull finger, your dirty washing, as it were, is exposed for all to see. And it means that in these very quite simple ways, people can see what's going, something which actually has required a huge amount of information and a lot of networking, but it's available. It's, as I say, it's democratizing environmental information, and it's giving it sort of quasi real time. So this might be only a few hours behind what's happening. So it's not one of these things where you get a historical report years down the track. It's to sort of do something now. So if you have got controls of, dams and whatnot, you can make decisions which could improve the situation. And because it allows you to learn more quickly. As you accumulate this data, you build models, and then your models can be used to say, well, under these conditions, what flows will need to get this level of dissolved oxygen or whatever. So interesting about this, it's a big company partnership between AT&T and Ericsson, and they actually started with sort of what I would call the older technology, third generation, because they wanted to get the runs on the board before the latest LPWAN technology came along, and they're looking to modernize that with technology I'm going to describe in a minute. An example closer to home, a company called Splash Energy in Auckland. This company uses sensors and communication techniques. It's wired in most cases, and they present the data of what they're doing quite an elegant way. So this is what they do. So it's a little animated graphic. This you can see isn't live, because the live one is difficult to manage, but this was taken at night, hence the PV input being 0 kilowatts, in case anyone was wondering, the sun has stopped in Auckland. No, it's not. But what's interesting about this display is it's kind of light and accessible. Again, it's democratizing the information, but it's sort of giving you historical information. What have you done to date? It's giving you contemporaneous information. So what is the state of it now? So should I turn the washing machine on, or the dishwasher, or do the ironing, put the jug on? But it also gives you a feel good, what environmental impact you've done, how many car kilometers you've saved by having PV on the roof. As it gets more sophisticated, these things evolve. They'll have the information, we'll decide based on the weather forecast, well, shall I put the energy into the battery because I'm going to have cheap energy tomorrow, or should I use the energy now? And because these things develop, then those systems become with a greater degree of autonomy, and it really adds smarts into these models. And this isn't a large industrial model. This is something that happens at a domestic scale. And as I said, it makes it relatively easy to see if you've got people to put this up, and you can easily see what's going on. And generally speaking, it's observed that if people have good information, they make good real-time decisions. And I know that for some of the renewable energy projects I've been involved with, where people know the wind's blowing and they've got wind turbines, then they'll use the electric jug. And if it's not, they'll use the gas. And just simple little things have both an energy impact, well, an environmental impact as well. And so I'm going to now get to the sort of what's been the focus of what I've been looking at recently, which is these low power wide area networks. So what I like to say, that this extends the internet from the factory to the farm, or wherever you want to put it, the environmental predator-free scheme, whatever you're doing. Because what this enables you to do, it enables you to transmit data over a long range of relatively low power. The key point of difference is that this technology is the first one that's predominantly for data only. It's not based, apart from the narrowband IoT, it's not associated with telephony. And so in that sense, it's kind of breaking away from the old models. And that's not just in terms of technology, it's also in terms of business. And it's kind of interesting how it goes. It's a disruptive effect in that new businesses are coming in. Some of whom have never been involved in telephony. They're just effectively data-only service companies. But a lot of the telephone companies and the cellular companies are actually seeing it's a real opportunity for them too. There are three options. There are three main options. There are other options, but the three main options are Sigfox and LoRa and narrowband IoT. And I'll explain a bit more how they vary. But the Sigfox is, as a technology, I liken it to the old-fashioned telephone system. You remember the telephone systems before there was competition? No matter what kind of phone you bought, you plugged it into a telecom port. So you could buy any phone you wanted, but you always got served by New Zealand Telecom or a British Telecom if you were in Britain years ago. And so that was simple. There was very little flexibility, but you knew what you got. You got what you paid for, and it was usually just sufficient for what you wanted. So that's like the Sigfox model. It's simple, it's easy to use. There's one franchise for the whole of Australasia. So if you develop your Sigfox application here, you can take it to Sydney and nothing to do. LoRa is more like the modern telephony system where you can have different people providing both ends, both the cell, the network, the node end, and the server end. And the node, you can choose which LoRa system you're going to terminate your call to. And Spark just announced the week before last they've rolled out their national service for this, and there are other companies who are providing services at the moment. Those two both come from France, incidentally, and they've been out for more than 10 years. Narrowband IoT is the telephone company striking back, if you will. It's a higher performance system, still not commercially rolled out all around the world. There's test sites in Melbourne, Sydney. There will be some test sites in New Zealand soon, and there have been some tests in New Zealand, but it's not publicly launched. That is a higher bandwidth system. It's a different kind of service. But in some ways they appear in the same bucket, and they all identify themselves as LPWAN technologies. Quick comparison between the LPWAN and the rest. So the blue is the zone that the LPWAN offers. So it's got a long range. So we're talking about potentially up to 10 kilometers or 30 kilometers. The longest I know that Sigfox has done is over 200 kilometers, but that's absolutely ideal conditions. So don't anyone say it does 200 kilometers. That's an extreme case. But it's in the urban environment. We've made measurements ourselves. They're good for a couple of kilometers, and if you've got enough base stations, you just ride seamlessly across town from one zone to the other. You've got service. So the geographical coverage and penetration is quite broad. So it's up to the left-hand side there. The range is long. It's the top axis compared to the red line, which is the incumbents. This is the 3G, 4G, and 5G traditional GSM type services. There's a whole range there. The Zigbee, which is the wireless Ethernet, sort of sits in the middle. The transmission latency is relatively high with this data-only service because it's not a telephony service, so you don't need instant sort of duplex feedback, so you won't get a message back straight away. Whereas the telephone systems will do it. The key thing, I think, is that the cost, the radio subscription costs, the power consumption are relatively high with the traditional systems. So it's quite hard to put a system into the field based on a 3G network and say it's going to go there for 5 years unattended and just run, because you'd actually have to get a power source to it. The other thing is that the bandwidths differ a little bit. So the Sigfox is roughly 300 bits per second. The LoRa ranges from 300 bits up to 30 kilobits per second. So these are not video bandwidths. These are quite low bandwidths. The narrowband IoT is up from 200 to 750 kilobits per second. So that's a much higher bandwidth service. So that's why I think they're not direct competitors, but they have they overlap significantly. Oh, it's interesting. This has been reformatted. Obviously, this screen isn't quite what I did before. Sigfox, as refresher. So Sigfox is a simple one supplier in Australasia. LoRa, they come through Spark, or Kotahinet is a private provider in Canterbury and some other places. Or you can decide your own. You can decide that you're going to manage both ends of the network, and you can build your own system. And we have got a system in our office that we can do both ends of the LoRa connection. And narrowband is the highest bandwidth service, and that is coming soon. And when it comes, it will be backed by a lot of money, and it'll be a serious service provider. And I think it will meet the needs of a lot of clients who currently use cell phone-based systems. So if you're interested in these IoT technology, essentially you've got three choices. Actually, I must get something out of my bag. You've got three things. So you can either decide that you're going to go to a turnkey provider, someone who can provide what you want, and they will just deliver it out of the box. And that way you get a straight measurement. So if you just want to, say, measure soil temperature, you can just do that. You can ring up today. You can buy a sensor, put it in your field, pay for the service, pay the subscription. And with the LoRa and the Sigfox, still at quite low, just a few dollars per 12 months. So quite a low-cost service compared to dollars per month, probably for a telephone system. You can develop your in-house service. If you've got electronics already, you can just do it, and then you just extend your electronics capability. Or you can come to someone like us at Callaghan Innovation, where we have a We've got some experience in testing these things and actually making services that work off them. So what we decided, what we looked at this and we said, what are the needs? And one of the needs we realized, to make this work, you need really low power. And to have low power, you've got to be able to manage the node very effectively. And we also said, look, we want to learn by doing. So we wanted to know how Sigfox works and how LoRa works and narrowband IoT when we can. And our role is to, as I said before, is to facilitate the acceleration of these things into New Zealand markets. So we're not producers of systems, we are developers helping producers. And so what we decided to do, we would make a low power system. I've got an example of it here. I'll just turn the LED on it. Which actually is based on Arduino technology. Now, for those of you who are technical, I can provide more information, but essentially we picked that because it's an off-the-shelf technology and we can do very fast prototyping. So what I've got here is, this is what I have in my hand, is what you see on the screen. So this is a tiny wee board. It's actually got an Arduino footprint, so we can plug Arduino shields into it. And what I've got here is a Sigfox shield. So this is effectively a Sigfox compatible device. The key thing to point out on this photograph is that the two little squares, which are much less than the area of my thumb, are the key components. They are the processor and the real-time clock and a couple of crystal chips. So we believe we can make this a system little bigger than a postage stamp that will be able to deliver node processing and then connect to a wireless interface of choice. And their expectation is that people will use something like this as a prototype, get their particular signals, what they want to do. There might be acceleration, might be temperature, might be humidity, some combination of the two. They might say, well, I want to know what the peak is. What's the peak temperature been in the last 24 hours? And then you've got two ways that we see this transmitting. So one is it has a regular event. So every day or every week, it signs in and says, hey, I'm all good. This is me. So it tells you what you identify. It's got a unique identity. This is the state of my battery. That tells you how long it's going to last. And then whatever parameter it is of interest, it reports a few bytes about that. So we're only talking about a few bytes, so 16-byte packets of information sent maybe 14 times a day. Oh no, a bit more than that. Sorry, it can be more than that. But to save power, it will only send the message once a day unless you have some critical event. So suppose you have this monitoring seismic activity under your house. For years, it's going to say once a week, I'm good, I'm all here. When there's a shake, it's going to wake up straight away, and then it's going to start broadcasting. On the back of this one, you can see there's a little battery. On the back there, we can put up to a 1 amp hour battery, 3.3 volt on that. And depending on the application and the software programming, because there's options on this, we believe that could probably last for 5 years. And so there's applications for this where we're going to see it completely molded into a piece of equipment, no serviceable items at all. It's just part of the package. It doesn't rely on the user connected to their Wi-Fi. It doesn't require any sign-in. It's entirely transparent. We talk to people who can see value in this in heavy machinery, where machinery goes into the field. Talking to someone the other day who has a machine that does great things in the forest, and it's quite an elegant piece of machine that does something, and they found it was experiencing these huge pressures. It was a hydraulic system. When it got down to it, somebody was using it to straighten the logs, just banging the end of the logs on the truck. Now, of course, what happens, that's a warranty claim when it fails, because you can't prove the guy abused it. But of course, if you had something that was measuring the pressures, and you keep seeing these extreme spikes, you say, okay, I'll just snip out and see what's going on. So there's a lot of things where having it being completely autonomous is a real benefit. Because of the nature of the LoRa, it's quite low cost to make your own base station. So if you're in some remote location, you might take a base station out to where you're doing the work. So it might be in a forest or in a mine or whatever. If you're in a place where you've got Sigfox coverage, so you might be in a regular rural area or an urban area, then you don't need to provide your own base station. And we expect that customers will do whatever's best fit for purpose. The other one, I talked to someone who has a company, a transport company, and in that company they have dangerous goods pallets, and these are quite expensive bits of kit. I mean, people think a pallet's a pallet, but it's actually several $100s. And these things are too cheap to warrant GPS tracking, but they really like to know where they are and what they've been up to. So if you imagine you're transporting something which really mustn't get above 60 degrees, be quite handy to know what the temperature is continuously. And if it got above 65 degrees, send a message, say, look, this thing has been parked in the sun all day, driver's gone home for a smoko, like extended smoko, and the refrigeration's broken down. So instead of finding out that everything's ruined or think it's become dangerous, straight away, maybe you can take action. Maybe you set it at 55 degrees to say, call the guy on the cell phone, do something, check this. So there's a lot of value adds that you can do by embedding the smarts. And of course, that's just one case. The real value is when you can aggregate this data over a fleet of items, and then you can see the usage. You can see when you've been over designing, or you're very close to under designing, very close to warranty claims. You can see how people are using your product by measuring simple parameters, acceleration, temperature, humidity. And then you can say, well, okay, what people really need, because they keep failing because they're experiencing these conditions, they need something that's more robust. Or they need something that's, we need more information about orientation or handling. When people are dropping these things and they shouldn't do because they think they're tough enough. And so we see this technology, not in this form, this will just be prototyping. One of our next generations we hope to do is to put this on a flexible circuit. So it'll be no more than 1 millimeter thick, and we'll be able to mold it and flex into any shape you want to put it. And then the antenna won't be one of these things, it'll just be a piece of wire that's molded into whatever the product is. So this is this piece is our communications controller. So the communications controller is our design, that's something that we've made. And we've done that because we want to get experience, we want to learn by doing. I'll pass it around. There's unfortunately not much to show, but if you want to look at that, I should say that all the wires at the end, all these jumpers are just so that we've got all the options, so we can break out any configuration. The expectation is that when you have a final design, you just pick the ones you want. The final design wouldn't probably have Arduino connectivity to it because it wouldn't need it, but if it did need it, we'd just leave it there. So I guess the other thing, and I've hinted at it already, I should say that when I prepared this talk, there were other colleagues going to talk about artificial intelligence and machine learning afterwards. This is the segue to them, but it actually fits to this, is that when you've got this data, you've got data coming in from around the world in different forms, whether it's connected or whether it's wireless or LPWAN technology, you've still got to do something with it. And there's a lot of work on artificial intelligence and machine learning. I've got colleagues in Auckland who are particularly, I was fascinated to learn that they've got systems now where you can give it a set of data and you don't give it any clues at all. You just throw this piece of software at it and it works out the patterns for itself, and then it works out the exceptions to those patterns. So it doesn't matter what it is, if it's medical, biological, it could be anything. If the data set is rich enough, you can just let the software find out what the pattern is. And then it says, well, it usually does this, but this is the anomaly. And then, of course, you as the designer get to say, well, okay, well, what causes that? So go right back to the specifics. That means you can find the needle in the haystack, which has often been the problem with big data. For many years, we were very data poor because SCADA and the like was expensive, and in particular the energy system. And so you just had the minimum. And storage was relatively expensive, so you used it, you discarded it. And then we started to store it, so that precious data accumulated at a slow rate. And then with the ability to store really cheaply, people said, well, let's store it. I heard of one company, I obviously can't name who they are, but they dived into this years ago, and they're collecting 10 gigabytes a day worldwide, do nothing with it. They're just spinning iron ore somewhere, just collecting these bytes, and they don't know what to do with it. But they feel there's value in there, and there's every reason to believe there is. So you had this, you went from famine to feast in terms of data. So now there are big data sets, and now people will say, well, how can we get value out of that? And then you go on from that. You say, well, once you've made sense of the data, you're going to derive value. And that's really what Industry 4 or industrial IoT is really about. And one of the things that people are talking about, which I find fascinating, is this concept of the digital twin. Is there anyone who's heard of the digital twin concept? Okay, I'll just give you a quick. So the digital twin, the idea is that if you've got a piece of equipment, lots of instances you've got in the field, and you want to know how it's going to behave, how you can improve its design, you have for the sake of argument, let's call it a hydraulic ramp. That's kind of easy to imagine. It's doing mechanical work. It gets abused and used in lots of different ways. And if it fails, it can fail catastrophically. It can have fatal consequences if it fails badly. But it's essentially a machine where you put energy in and you move energy, transform energy in it. And if you've got a model that is a finite element model of the mechanics and the hydraulics, you can say, this is what it was ideally designed to do. It applies this much pressure, it does this much energy, this much efficiency. Its efficiency means that it will warm up, that heat has to be dissipated, and you can do 100,000 cycles and say, what should the steady state temperature be compared to, difference from ambient? And that's really cool. If you then put sensors on these machines and you take them out to the real world, it then enables you to say, well, how good is my model? So your model can be improved. But then once you've got a model that reflects the real world, you can then make virtual sensors in the middle of hydraulic fluid where you can't possibly put a sensor. And then you can sort of ask the model questions. And if you get a failure in the field, you can take the thing apart and say, well, why would that fail? Why might that have failed? It might be a crack here. You go back to your model, your digital twin, and say, well, let's simulate a crack here. If I run the data forward, do I get the failure? So the digital twin is a virtual machine which sits alongside a real machine and allows you to do both historical analysis, failure analysis, so like a black box, but also start to use it for predictive analysis. So you can say, well, okay, let's say we're going to change the material because we can save some money. Now let's run it forward, do 10 years life in 2 or 3 weeks modeling. Where's it going to fail? Okay, so then you decide, well, do I like that? Is that an acceptable life of product? Or I say, no, I can't do that. I need to reverse the change or change the material. So the digital twin gives you the idea. It's the sort of it's industrial virtual reality, but actually providing value. I can think of, see Bill at the back, wind turbines. There's a huge amount of stress in those things, and a lot of work's been done. And there's a lot of exotic materials that are used to improve the weight to strength ratio, to maximize the strength per unit weight. The digital twin allows you to push that boundaries further faster. Because instead of having to do 5 years of lifing, because obviously you don't want a turbine blade flying off and with all the damage and the PR loss of brand damage here, you can actually say, well, I'm going to run this, I'm going to do my 5 or 10 years or 20 years, 50 years of action on the digital twin, and then work out what I should do. And then say, I might decide, okay, well, they need to be inspected more often. I might not do anything to change the design, but actually this looks like there's a weakness. You can see Air New Zealand this week having big trouble with their Dreamliners, because someone said, oh, this turbine blade, now have to inspect it every 200 hours rather than every 3,000 hours. And thousands of New Zealanders are going to be interrupted in their travels because of that. So what they're doing is they're saying, we're going to preempt the problem by using what we know from the models to say we should check these things. And I suspect that applies to lots of energy systems, because the alternative in the past has been to over-engineer. All you could do is to say, well, if this fails, it's so catastrophic, we've got to have a big factor. So it might not be a factor of 2, it might be a factor of 5. And so you end up putting massive resources up front for which there is no payback. It's just wasted money. So instead of doing 2 big systems, you can only do 1. So what it means is your capital investment can be made more intentionally by actually knowing what you're doing. And you get to play with time, because with the digital twin, of course, you can accelerate through and do years of stressful conditions. The thing can be in a permanent hurricane for a month, which would take years in real life. And I suspect that that the digital twin is one of the top outcomes down the track. And where I started talking about IoT, so that's really a fruit of the IoT. In some ways, it's along with augmented reality, is where the real value is going to come. It's where society is going to be able to make better financial and business decisions. And that those who've got it and got that ability will be the ones who will be the winners in the long run. So that's a quick scan over IoT. If anyone, I'm going to finish my thing. So if anyone's got any questions, I want to say before that, if anyone wants to know more about the technology of that little board, I've got hidden slides in here and I'm happy to share them. They're not commercial in that level, but I don't want to bore everyone with them if they're not interested, so I'm not going to put them up. If anyone wants to, we can just have a private look. And if anyone got any questions about anything that I've said or...
Right, Robert.
Yeah, thank you.
Sure, there's questions.
Yeah.
Mark, any tips for a large organization that's afraid of the cloud?
It's a serious tip, is talk to us. And the reason I say that is because we're neutral good officers in this. We don't make money out of the cloud and we don't sell cloud services, but we do support companies who we have a relationship with in their provision of services. And my colleague who was talking yesterday, he showed the Gartner curve of hype. I wish I had that slide. It's a beautiful slide. And it goes up, and at the peak of the hype curve, it's all promise, and and then the slough of despond comes when you actually come back to reality, and then you climb out, and you actually see some progress. Now, some of the machine learnings are right at the top of the hype curve, and so in that case, you need to know exactly why you're doing what you're doing, and know who's helping you do it. And I'm not an expert in that, but I know that we have people who are. So that would be the thing, would be get some advice, get some impartial advice, not just from us, although we can help you, but I would engage, I wouldn't run scared from it, because the companies that are making it work for them are doing very well from it. But it is horses for courses. It's not a one size fits all. So that would be my, get some good advice, but don't run scared of the cloud. And I guess the other thing is, it's always about business process. Ask yourself, what is the business reason for doing what I'm exploring? If that doesn't stack up, then, do well until it does. Yeah.
What are the options for really remote sensing?
Well, the satellite's definitely an option. The satellite is sensitive to the market. So the cost of satellite services is coming down. We were looking at predator, checking for predator traps. That still the most effective way of catching a possum is to capture a leg trap and then bop it on the head. It's hard to kill him humanely with a cost-effective trap, but if you don't get there in 12 hours, you're up for a $20,000 fine. So now there's a lot of people go in the bush to check these leg traps, because if they don't, if someone finds a possum struggling, they could be in real trouble. And so satellites is still probably the go-to method for remote applications. But with the LoRa system, it's quite conceivable to make a repeated set of broadcasters. That's one of my ideas. I'll share it for nothing. Is that we could design a LoRa base station right next to a LoRa node, and then they just chain automatically. You haven't got to do anything. And then all you need is quite a modest solar panel to charge that up, and it would go pretty much in perpetuity. So I think LoRa offers a solution, and then it's just a question of working out if you want to own the cost of maintenance of that backhaul. That is a cost to you, until you can convince a service provider to provide one, and they're talking about doing that. What is it? A base station that isn't actually a telephone system. It's actually just the data, but that's not reality yet. Yeah.
Mark again.
If anyone wants to work on LoRa stuff, the university does have a LoRa network running for about 6 months.
Yep.
It's working really well.
Good.
Try new sensors or work through teething issues.
Yeah, cool.
So for those of you that don't know, that's Mark Mason from the energy side. So feel free to come through us. We'll get in touch with Mark.
Certainly.
That sounds like an opportunity.
Definitely. Sure. Someone else had a question. Someone was putting his hand up. Did you have a question? Yeah.
So when do you mean about the low power? What do you mean the power needs to reduce the power consumption for sensor side?
Low power means to minimize the power from the whole sensor system. That's both the sensor itself and also the transmission side. So there are some sensors which are intrinsically quite high power, and so then the smarts have to be to turn that sensor right off. So it means just shutting a sensor down, it's a high power sensor, and then only bringing it up when you want to. But you can have there are accelerometers which have quiescent power of less than a tenth of a microamp. So that you can afford to have on all the time, a tenth of a microamp. And the cool thing about these systems, they're designed to be able to wake up. So even at that current, they have a threshold where if they exceed a certain level, then they wake up the system. So there's two things. So one is the management to turn things off, including the transmitter itself. So the expectation is that these things would be in the quiescent state, the transmitter would be shut off and would wake up either at the time event for a routine check-in or for an exceptional event, broadcast, basically compose its message, broadcast its message, and after 10 to 15 seconds, shut down to the quiescent level. Now, the exception to that would be, for instance, the seismic thing, whereas if you imagine you have an earthquake that's hopefully not going to happen, but if it happens once every 5 years or 10 years, when that comes on, you actually want to record a lot of data. So you might have a battery that's good for 10 years that will get reused up in 5 minutes, because then you want to record everything and you just accept that, to get the richest data, you sacrifice it. But the system that's well designed should allow the user to choose that. So generally speaking, it should be quiet unless the user wants information now. Does that answer your question?
Yeah.
Yeah.
So because I'm working on system alerts, I think this kind of thing is pretty mature for system devices.
For sensing what?
Research has been done on how to reduce energy consumption.
Yeah.
For example, allow for slave rental, and we have for sharing.
So what are you sensing in that? So what's the sense?
I mean, it can be any kind of sensing like temperature.
Yeah.
I mean, for the sensor side, the main solution to share the data to reduce energy consumption. What do you, I didn't get what you mean about low power wide area inverters. Because for the sensor side, how to reduce energy consumption to the research.
Yeah, that's right. Yeah, that's good. And so it's just a question of picking the right sensor to do the job. There are some things where the sensors are intrinsically quite energy intense. If you're using ultraviolet to monitor nitrate levels in water, you've got to basically put on an ultraviolet LED, and they're not super low power. I mean, they're low power compared to a laboratory laser, of course, but they are relatively high power. So then all you can do is turn them off to reduce the power. But I guess what we're concentrating is not on the sensor side. We're concentrating on the data processing, the local processing of data, and then the sending of that data to the back end. So we're not, yeah, you're right. We just pick the sensor which is appropriate, or recommend the sensor which is appropriate to what you can do. And so that's that one.
Excellent.
You don't say,
Michael?
I'm just wondering, with do they work both ways? Can you see the signal and the control?
There's some control, but all of them have some bidirectionality. With most of them, you actually the subscription goes up if you want bidirectional transmission. Not hugely. It's quite complicated. We've got a lot to learn about that. With the low RA, you've got quite a lot of freedom with what you can do with the download to the device. With the Sigfox, for instance, it's virtually impossible to upgrade the firmware of the Sigfox device. And nothing's impossible, but there's no easy way to do it. So that kind of, you commit to pretty much getting it right, committing it, and living with it, really. With the low RA, there's more freedom to send bytes down, and you can upgrade those. With the narrowband IoT, I'm pretty sure there'll be a lot more bidirectional bandwidth, but it's still predominantly a node to cloud direction. Yeah.
We have 1 minute, so it's a really quick one.
Yeah.
Worried
Sorry.
about nervous lecturers
Yeah,
outside.
right, yeah, sorry.
A very, very quick question. Thinking of the commercial area, and I would like to sense my flowers traveling somewhere.
Yeah.
I want to know this quickly. How expensive is it going to be, thinking that once it's done, you can never recover it?
Well, of course, it's always hard to say at this stage, but my expectation would be, if you had a simple sensing, like suppose you want to sense humidity and temperature, and you want to have a low LPWAN connection that's within this box, and you're prepared to fit and forget, to last for 5 years, you're probably looking at a unit cost of low hundreds of dollars. So maybe I'm just guessing now, completely guess, $250.
Mm-hmm.
That's what I'm looking at. So not looking about tens of thousands of dollars, and you're not at the moment looking at sub 100.
Mm-hmm.
Now that would change if you were wanting absolutely, millions, real commodity product level. But
yeah,
that's probably That's okay. Cool. Thank you. Thanks very much.
I'm conscious we're out of time. If we
you.
could show our appreciation to Robert.
Thank you.